All right. So let us quickly start and try to finish off with the remaining portion of essay A512. So if you remember on last class, we had started with this cryptographic hash function with a specific requirement that we have in this an 80 set of words, and we found out the way in which this 80 words will be generated or a key expansion strategy that needs to be adopted. And in that we have observed that we are supposed to use a formula of this nature which was approved over here, and in that this will be a specific set of arrangement for the for the words starting from W16 to W79, and the following arrangement will make sure that the extra words are generated. As I said, this is very similar to the AES algorithm where we did a key expansion strategy as well. And today also you will find there will be another algorithm which is the Whirlpool algorithm, where also you will find very similar kind of approach there itself. So based on that, we found out that ideally this ROT function is not only a ROT function, but it's a two rotation and one shift also will take place, and that was proved by this example. But what I meant for this is that this is only a part of our discussion on the key expansion. So the overall algorithm will be looking something like this. This is where we ended our discussion actually. And I told you that the algorithm SHA 512, it starts with the initial condition of a certain amount of 8 words, which are given by A0, B0, C0 up to H0. So this is basically the initial condition which is provided in a tabular format. So initially this message, this is the 80, or if you can call it the initial digest that you are, or rather initial hash function that you are generating. Based on that, there will be a connection in this particular order. You can see they are very, like, it's not that difficult to understand, to be honest. They're all like directly connected. If you check the black color line, so A0, B0, C0, it's directly connected to round 0. Now what happens in round 0 is the discussion topic for today, as well as if you observe that it repeats till 79 and it requires the W0. So we know the process of how this W0 to W79 are computed, right? The equation, the previous this class. And this K0 to K79, this is also a constant. Okay, this also has a table from where you will get this 80 constants. So we will all use that to this round itself. Now what is inside that round? So that is what our discussion for starting is. So the rounds are looking something like this. Alright, please make a note and just make a note in the sense like you focus on the process that is involved. Now if you observe that each and every round will use those initial 8 words. So if you see in the very first, we have A to H over here. So the initial value, suppose this is my round 1. For example, this is my round 1. So the initial values of A, B and all are A0, B0 to H0. Now you observe that somewhere in the middle there is something called as X C below and Y C below. It means that there is some operation that goes in exactly at this point. The rest of the bits are just shifted. You can see the rest of the bits are not that difficult to understand. It's just that P is shifted to C, C is shifted to D, E is shifted to F, F is shifted to G, and G is shifted to H. So there is something that happens other than that. So that is what is explained over here in this particular block. So both of this block, you can observe that there are 2 segments to it. So one segment deals with the bits A, B, and C, and the other, and also you can see the next half deals with E, F, and G, and the H is taken care of by a element. So we are actually dividing this into 2 specific operations. Each and every round of that 79 rounds will have this particular configuration. Understood? So if you observe the left hand side, if I just focus on this left hand side, okay, if I call it the L1 and this I'll call it as R1 for my references. So if you observe, there are 2 basic functions that is going on. One is called as the majority function over here, which involves ABC, which again will be a binary function, nothing more than that. Combination of a certain element. You can see at the bottom it's mentioned over here. It's a combination of the inputs for the binary function. And along with that, there is a rotate A. And rotate A also is given over here, how it is to be rotated. And this is also constant throughout. You can see the first thing is rotate the 28 bit. Can you see that? Here the mentioned. I don't know whether this is write it down otherwise for you. It's mentioned here actually. Rotate the 28th bit of the A word. So that is what is mentioned over here. So the rotate bits of word A by 28 bits. Sorry, it's 28 bits you have to rotate. Same way, see over here you can see X by I bits. So that means now the next one over here is 34. You can see here 34. So that's I mentioned it over here, rot 34, which means right rotate the bits of the word after that first rotation by 34 bits. And same with 39 bits. So basically, each and every time you are taking ABC, that goes to the majority function and that generates some kind of an output over here. And the rotation function will generate another set of output, maybe output prime. And both of those two outputs are getting a element over here, which is we call as the modulo addition. You can see here of 2 to the power 64. So I'll repeat once again what is exactly happening. This is what we are discussing about each and every round under SHA 512. Within that, we are starting with the 8 words A to H. Now, based on that A to H, except for A and particularly the T, rest of them are shifted accordingly based on the diagram. After that, individually, the A, B, C are subjected to some kind of a function where the left hand side, L1, is given by majority and a rotation. These are the two functions which are used. Majority applies on ABC bit or the ABC word, and the rotation only happens on the 8th word. And that rotation also happens in the form of 28 bits, 34 bits and 39 bits. This applies over here as well. In the right hand side, if you observe, there is another rotation there. But in that case, the word is E. But again, the 28, the 34th and the 39 bits are rotated for the E word as well. So that to rotate A and rotate E remains the same. That's why it is given here, rotate by X. You can see the bottom, it's mentioned over there, rotate X. Alright, so the rotate function same in both L1 and as well as R1. And if you observe over here in the right hand side, we have a new segment which is conditional, and that also is given by a binary function over here. X and Y and not of X plus Z. So X, Y and Z are used over here, where X and Y and Z, which is mentioned over here as E, F, G. So basically in the right hand side, we are considering E, F, G as an input. That goes to the conditional part, that's why it's mentioned E, F, G. The H remains intact, that goes over here as well. Rotate E is the same as that of the rotation is mentioned over here. All this through goes through this modulo operator, and finally we are generating an element over here which again gets mixed. Alright, so this again, both the output of L1 and output of L2, R1 is again getting a modulo addition of 2 to the power 64. And finally we are getting an output over here, and finally we are getting output over here, and these outputs are basically, you can see, can you see this carefully? If I remove this, area, see here, Y is the right hand side over here. Just observe carefully. This input to E, can you see it? Input to E is nothing but this element. This part of it, you are getting here, is basically the input over here. You can see there is no input. This arrow is missing. So this while operation is basically what is going on the right hand side, and the output which is generated here is fed as the input to this EH word. That will be my E word. And same way, the A word will be the output over here. See here, to A. So B, C, D and E, F, G remains all intact, except for the A and T, that A and E rather, those are generated by this majority function or the conditional function along with the rotation. So each and every round will undergo this strategy and will generate a specific amount of bits or the key set, which will look something like this. So this is basically, if you observe in the right hand side, if I go back to the previous diagram, if I just go back to the previous diagram, we are focusing here. Again, please focus on this. we are all focusing on the round. Okay, the explanation that I've given right now is basically round. So in round, what are the two other inputs? One is W naught, the other one is K naught. You can observe over here W naught and K naught coming in over here. So on the right hand side of the segment, the W naught and K naught gets modulo added to that of the output, what is coming after that condition and rotation function. Alright, so that all together will form each round. So now if you check here, so each of these 79 rounds will have, or 80 rounds will all have the similar pattern of generation. This is nothing but a function here as given over here, x and y we have to do. Then we have XOR of not of x and z. So it's the opposite of x, whatever is there. Right, so that is the function given. So this whole thing that you are looking at goes to each and every round. Right? So let me go back to the PPT once again and let me just show you the segment which is there in the PPT so that we can understand that. So this already we have done. So this is basically the initial A0 to H0. Now we all observe that the initial starting we need a element. So that is given over here. This is the block, same block diagram. Now you can understand that this is what I was explaining in the other segment. So each and every round will require a W0 and K0. Now W0 is generated by the process as described over here. Okay, so W0 to W16 we don't need to worry because each and every case 16 words are initially there. But post W16, like W16 to W79, we have to generate using the key expansion strategy. Alright. So this is what the structure is. This is the structure again, same way. We can observe that this is basically the key expansion strategy, or rather the generation of the structure of each round for that matter. So that is being given over here. This table indicates the K0 to K79, the constant matrix that we are going to XOR at the each and every round. So these are the 80 such words. There is a rule to generate also this one, but I'm skipping for the time being. But these are some standard values which are given. They are also generated from the prime numbers itself. Okay, we can find out how this is made also. But these are the standard. So if you are in round 0, suppose, and you need K0, you will take this one. If you are in round 1, you will take K1, so you will take this one. Like that, each and every time it's a constant matrix that we are going to take. Right? So that's how it should be. So these are the functions which we already had discussed, but this is the kind of a summary of it. Okay, of the majority and the condition and the rotation function. If you observe, these are the functions, ROT 28, 34. Right, so these are the three functions. So please make a note of this. Please understand this question very carefully. It's utmost of importance. So there are K0 to K79, which are the constants, which we are talking about, the constants. As I said, they can be generated. Okay, now the generation I'm not discussing as much, but just keep the rule, just remember the rule. One rule is to find out the K0, we are taking the 80 prime numbers, starting from 2 and ending to 409. This is very simple, it's not that difficult actually. You don't need that also. So 2 to 409, these are the total 80 prime numbers. Now the process is, for the prime numbers, you take the cube root of it. Whatever the value you are getting, you change it to binary. And the decimal equivalent part, you convert that to hexadecimal. And if you observe the 6C44198, this will be one of the key which is present. So this what we are doing it for the 409. That means it's the 88th word. Right. If I go back to the table, the last word is like that. That's what I was telling you. All these 80 words can be generated using this process. 80 prime number, take the cube root of it. Okay. Change it to binary. The decimal part of it, convert that to hexadecimal. And the hexadecimal number will be the key that is built there. But as we don't need that, so I've skipped that for the time being. Even the A0 to H0, initial value that we are talking about, that can also be generated. How? In that case, we will take the range between 2, 3 to 19. All the 9 up to 19, because there are See, 1, 2, 3, 4, 5, 6, 7, 8. A to H, 8 words, 8 prime numbers. First 8 prime numbers. Same way, you take the square root of it. Instead of cube root, you have to take square root of it. And then the same way, you convert that to binary, take the decimal part of it. Whatever you are getting over here is basically my 80, or this is, if suppose this is 19, that will be my 80. Let me just show you that also. This one. So if you are trying to find out where this A0 comes from, this will be 2 square root of it, whatever you are getting, convert that to binary, change it to hexadecimal, the decimal part, you take that should match this is A0. Similarly for 3, you get this one. For 5, you might get this one, like that, so on and so forth. So all these 8 elements that you are looking at, these are all from the prime numbers, and similarly, this table also is formed from the 80 prime numbers in the cube root process. So one is done using the square root, the other one is done with the cube root. Just remember it. No need to panic in that, because we don't need to follow or solve it, will be provided to you. It's just a technique I'm telling you. The important part is this. Please understand this question very carefully. It's a very simple process, and don't lose out scoring marks if question comes in of similar nature. The question is, we apply the majority function on buffer ABC if the leftmost hexadecimal digit of these buffers are 7, A and E. What is the leftmost digit of the result? So we are applying the majority function. So the only thing that you have to remember is how the majority function has been defined. A and B, XOR B and A, C, XOR C and A. So what you have to do is, you have to just change this number 7, A and E to corresponding binary numbers, and take each bit one at a time. Because there are 3 bits A, B, C. So take 0, take 1 and take 1. Substitute in the function. Whatever be the resultant you are getting, substitute and mention it over here. Am I okay with this? Very simple. This is very simple part of the journey. We have given any data over here, whatever be the data, convert that finally equivalent. Take each bit at a time. Substitute in this equation. Okay? Find out the corresponding result over here. So the final result after this majority is coming as this, or we can say like this. The only task that you have is to remember this as the majority function. That's the only task. As I said, in this particular module, we are not going to invest much on numericals, because it's very difficult at times to solve for 512 bits manually. So this kind of simple type of questions might come in along with the methods that we have discussed so far. So please focus on this kind of area. Similarly, conditional questions will also can come in. So maybe I can give you this one, a conditional function suppose. So it is given like this, 0, 9, A and E, F. What will be the conditional element? So you can see the same way the conditional function needs to be defined. Same way you have to consider E, F and G. So 3 bit at a time. So pick up the first letter from each of the elements. Substitute in the function. Get the final result. That will be your answer. Suppose instead of 4 bit, now we have 8 bit. Suppose I give you 8 bits. Same way you have to do it 8 times. That's it. And suppose in some cases there are common values, 0 values or something like that, then you are favorable enough. 0 plus 0 plus 0, something will come as 0. So you can do it very quickly. So the process, please remember, and how it is to be done. Remember, these are all the process or the function that is adopted in each of the rounds. Alright, so please make a note of this kind of questions. Okay. So even the shift function might come in. Suppose I give you a shift function, and you know that which bit, how many number of bits needs to be shifted, or the rotation. Rotate the 28 bits, rotate the 29 bits. So you just substitute the equation or the word and arrange the 28 bits one at a time. Simple as that. Nothing is, no calculation is there. Only the shifting of 28 such bits. So be a little patient and go on doing that process. Okay? Yes.
So the first bit and like substituting the
function. Yes. So that's it. Nothing else. That's why it's a very scoring area that you must focus on. Don't lose hope that, sir, I'm not able to understand the algorithm, because I know the algorithms are difficult. That's why they are still in use. It's not that Caesar cipher for that matter. Okay. That's why these are still being used right now in cryptography. So naturally it has some difficulty in cracking the scenarios, right? So definitely the algorithms will be there in that way. The process you understand, and this simple process of calculation, please understand this. All right. So now let me, yeah, please, sir. The task. 39. Where? No, this should be 39 actually. This should be 39. It's wrong. It should be same for both A and B. Please make a note. I'll change it later. It should be 39. It is there in the books also. It is 39. It's wrong type. Alright. Now we come to the next one, which is again, which you might get familiar, because this is nothing but the application of AES, which you already have done in your CAT 2, as well as we have discussed a lot of, we have given a lot of time to that. Whirlpool is a technique which actually deals with, or the process involves, Miyaguchi-Pranil scheme. If you don't recollect what is that, I have given one slide for that as well. Just to recollect on the applications of cryptographic hash function, there we had actually discussed this. The process was very simple. We have a padded bit of data, original message, which will be divided into certain blocks of certain bits, suppose here. And the only difference was that we were feeding that as a plain text. The H function or the hash function will be used as the key, and the cipher generated over here will be acted as another set of Zori, and the output of it will be fed as the key to the next, and that's why it is an iterated hash function. A Whirlpool, why it is important? Because that is what being discussed as the most advanced cryptographic hash function or the compression function which is available right now. Okay, so that's why we have to discuss a little bit on this, and the advantage of this is that this is very similar, or the algorithm works in the very similar manner as that of the AES. So just to give you on that, maybe I'll just give you, so this is basically this is the Miyaguchi-Pranil scheme, and this is basically the structure of the Whirlpool scheme. If you observe, both of them are absolutely same. 512 bits, block size is okay. 512 bits, so 80 is coming. So this is my key, this is my P, and this is my ciphertext. So the same scheme has been used over here as well. The only thing that is left to us is what is inside that Whirlpool function. Just like we had discussed, what is inside the SHA 512 function. Right? And it's very simple. It's observed there. This is basically, does it look familiar? If I give you this diagram, does it look familiar? Does it look familiar? Where is this coming from? AES. The same thing is used here, except that this is Whirlpool. What was the data set? 128 bits for AES. Here, 512 bits. That's it. Rest of the cases you will find, it will also have the state matrix. It will undergo shift operation. It will undergo mixing. It will undergo add round tree. So all the processes are the same. Except that it will be a little bit more, because 512 bits will require 8 cross 8 matrix. It won't be a 4 cross 4 matrix nowadays. It's again the bytes. 8 cross 8 bytes will be used. Here also the bytes concept will come. Remember, in AES also we have done the same thing. The words were considered to be in bytes. So here also the bytes concept will come. So that's why it's mentioned over here. So this is the basic structure of it. If you observe, there are 10 rounds. Remember, in AES also we had 10 rounds. There were different flavors of AES, but whatever we had discussed, it was only on 10 rounds. So here also there are 10 rounds. Right? So let's see the process. I think it won't be that difficult for you to understand. So this is the state matrix. Remember, all of you, the state matrix. We had done the words column wise, W0, W1, W2, same thing. Here, except you can see this is 8 cross 8 bytes. Size is a little bit more. And the reading is row wise. Please make a note of it. The reading is row wise. That means this is my reading style, not the downward. We will read this state matrix as this side, not downward. Okay, that's the only change. Because they had to come up with something new, so this is the only change. In case of AES, we were dealing with the column wise down. Here it is row wise down. That's it. So that's the only change that we are looking at. You can observe that B0, B1, up to B7. Again, B8 starts, so up to B15, like that it goes on. So the state matrix is of 8 cross 8 bytes, which was in case of AES 4 cross 4 bytes. Right? So what was there if I go back to the diagram over here, so we require a pre-round transformation, just like we had a pre-round transformation. For that, we will require some kind of a constant which will be provided to us, initial value. You remember the word, initial words we were provided. Here also, the initial K0 will be provided to us. So this pre-round transformation is nothing but the zoring of it. Each and every row wise, we are going to zor. Okay, so that pre-round transformation is same, except that in AES we were doing it column wise. First element column. Here, first row element. That's how we are going to do. Okay? Now we see the in between rounds. Similar to what we are looking at AES. If you see all the states and the substates, to be honest, they are all similar to AES, but this happens the same as in Whirlpool. We call this as a modified AES. They name it that way. So if you observe, they also have a sub-byte. What was there in sub-byte? We used to have a sub-byte table. Right? We were doing the row and the column as mapping. This is a sub-byte table for Whirlpool. Same thing, if you are having an element, suppose A5. So A is over here, 5 is over here, wherever it will intersect, D4, that will be your entry. Same logic. No, nothing new. Except the table is new. But the table also can be found out by a process which I am excluding for the time being. We can generate this table also. So the sub-byte part is that only. So this is my 8 cross 8 sub-byte, the pre-incubation stage, or you can say the pre-transformation stage. After that, the sub-byte comes in. The same state matrix now is over here. It goes to shift column. There it was shift rows. Here the arrangement is down size. Downward we are going to move. So if it is 0, because you can see they are all 0, 1, 2, 3, 4, 5, 6, 7. So this is the arrangement, right? This is the state matrix. So if your 0th column will shift by 0 element. Remember in AES, what was the strategy? The 0th row, how many shifts we have to do? 0. If it is first row, 1 shift. 2 row, second row, 2 bit. 3 row, third row, 3 bits. Like that it was, right? Same thing here, except that we are moving downward because the words we have considered as row wise. So we are moving downwards over here. So for the 0th column, 0 rotation. So 0 movement, you can say. First column, 1 bit downward. Second column, 2 bit downward. So the arrangement is given like this. Same operation, just the column wise we are doing, nothing else. So again, I go back here. So shift column, that's why the term comes in. Same way, we have something called as mix rows, similar to AES. Here, remember in case of mixed column, in case of AES, it was mixed column matrix, and there also we had a predefined template. Remember 2, 1, 3, 3 or something, 2, 3, 1, 1. Like that, it goes on repeating it. Same matrix over here. This is my template which is given as a transmitter. The receiver also will have similar kind of structure or some kind of a structure like this. But as it is not required, we have not given it over here. And if you observe here closely in this matrix also, this is also following the same way as it is being done in the AES. 1, 9, 2, 5, 8, 1, 4, 1. Next one, 1 goes shifted here. 1, 1, 9, 2, 5, 8, 1, 4. 4 goes up. 4, 1, 1, 9, 3 here. So it is basically the same structure as that of AES. In AES also we remember, right? 2, 3, 1, 1 it was there. Next column was 1, 2, 3, 1. Next column was, again a rotation happened. Same thing has happened. Except that the dimension is a bit more. And the process is same, as you can see. Row wise we are going to collect each and every element. And we are taking the column wise over here for the each and every column. We are going on multiplying the row element with the column, and based on the same kind of calculation that we have done in AES, we will find the final word, and based on that, we will found the state matrix which are supposed to. Fortunately, we don't have the calculations for Whirlpool or the calculations related to numericals on this for our syllabus. So don't worry. We will stick to AES only. No need to worry about this, but the process is same as that of AES. That's what I'm telling you. So now we are done with the mixed column part. So what we are left with is in the round, we are left with the add round key. Now this is where it is a little different to that of what the add round key was there for AES. What was there in AES? We had an key expansion strategy, right? We had that rot word, sub word, we were adding up each and every round, and one word was actually being used for the next word. Like that it was going on, right? So that is being used in a different way over here. If you observe carefully over here, this right hand side part, this is my key expansion strategy for Whirlpool. The right hand side. And that also undergoes a same set of sub bytes. Sub bytes, shift column, mix rows, add round keys. That is where it is different to some extent to that of what was there in English. And if you observe carefully, interestingly, what happens here, how it takes care of it. See here, the cipher key is used as the source, and the round output is being used as one of the constant or the key for that matter. And the same output is being fed to the next round. What I mean is that for this generation, it's a self loop that it goes on. You don't need any extra key to generate. It will directly generate iteratively a new key, and that will be used for the next round. And if you observe here, apart from these four substates, which are same as I already had discussed, sub bytes, mixed column, shift rows and all, shift columns and all, one very interesting thing comes in, which is RC1, which is a constant. So what we are doing is, we have to feed, this is my round, each of this is round 1. So round 1 will require the K0, which is the first round key, the given round key. The second round, so here in round 1, the additional K1 is generated from this output. But this K1 is also generated by these steps. Along with that, one RC1, which is getting stored in this last function or transformation. So this add round key is getting added with some kind of a constant. So how this constant is being? That's also very nice. So observe this. Is it okay how we are doing it? We want to have this K. Because that's, if I go back to the main structure, so K0 is, leave out the K0. K0 is the first defined one. So you need a K1. So what we are trying to discuss over here is the key expansion part. This one, the one I'm talking about. So in key expansion, what is happening? We are having this 4 transformation, but the last round over here will require some kind of a constant, which is RC1. So the second round will require RC2. Now, how to generate this RC1? It's very interesting. See how it is to be generated. You have the sub-byte table already, which is constant. So what happens is they follow a simple formula which is given over here. How? RC round, whichever the round we are in, for example, RC1, row and column, sub-byte table we are considering. For that, whatever is there in the sub-byte table, that should be considered. If the row is 0. And if the row is non-zero, we are all supposed to finish off with zeros. That means only the first row entry of the RC1 or RCX if I call it, or RCI if I call it, the first row will have the non-zero element. The rest of the 7 rows will all have 0 element. Because this is only when row is 0, this condition. The rest of the row is not equal to 0. So naturally all will be 0. So let's see for one at least example how it is to be done. For example, I am considering RC1. Please focus on this. We are considering RC1. That means round is equal to 1. So we substitute over here. Row is 0. Column is 1. Alright. Sub byte, sub 8 multiplied by 1 minus 0 plus 1. So what we get is sub 1. That means sub byte table for 0 row. So there will be column 1, 2, 3, 4 like that up to 7. So 0, 1, 2, 3, 4, 5, 6, 7. Whatever be the entry, this should be my first row of RC1. And the rest bits will all be zeros. So let me just show you that also. This will be my RC1 which will be generated where the first part is given over here. Rest are all Same we are deriving from the subbytes. No calculation. In case of AES, if you remember, W0 plus WA, some sorting was there, T0 was there, one temporary word was generated using rot word, subword, all those things, nothing is there. Here, its advantage is why? Because this is a very simple rule of doing it. If the row is non-equal to 0, or if rather it is equal to 0, we will take the 7 elements from the subbytes directly, depending on which row you are in. And the rest of the elements will be all zeros. Just like similar to the assumption when we took the padding. First bit will be 1, the rest will be zeros. Same thing over here. So that's why this is how the RC1 can be formed, RC2 can be formed, and that RC1, RC2 will get XORed with the existing state matrix, just like the row-wise addition or XORing, and we'll get the final K0. So that if I go back again, so this K1 is generated after that. So this RC1 is generated the way I told you, then that gets add round key, direct XORing, row-wise in this case, and we generate the key over here, and that again gets to the next state like that, so on and so forth. So for 10 round such, we will generate K10. Got it? So that's basically what the algorithm is all about. This is what the process is all about. You can go through it. This is basically RC3 structure. Although I find that this is wrong. The first row is actually not correct. As per my calculation, this is not correct. But this is given in book, so I'm just referring to that. But ideally, this is not correct. The first row should not be these elements. Alright? It should be something else. So anyway, so this is basically the structure of RC3. Similarly, the other constants will also come in the same manner. Finally, so this is basically what the idea is. So although Whirlpool has not been extensively studied or tested, it is based on the Miyaguchi-Pranil scheme, that's where we started off. And it is used based on AES, as I already had told you. In addition to the size of the message digest, same as for SHA 512. So therefore, it is expected to be very strong than one of the cryptographic hash functions. And this Whirlpool actually is to be used in most of the cases. Right? So this concludes the cryptographic hash function generation. So where we started, why we were discussing all this? Because we have a message and we have a hash function and the message digest is created. So all this process, the MD4, the SH512 and the Whirlpool function, all this does, what does it perform? It finds out what is my cryptographic hash function to generate the digest. For that, so many things we have done. So where we end our discussion today is something which I will start today and maybe on Monday's class we'll finish it off. That's the last segment of module 5 and that is called as message authentication code. Again, theoretical, no numerical, nothing should be coming over here. But this is also very simple yet very effective. What is this? What the idea is that suppose you are sending a message. Hash function, what it does is, it is saying that the message is encapsulated and we can verify that whether the message which was sent to you is actually correct or not. That's what primarily the hash function is doing. I am sending you a message. You can understand, okay, the message has been received as it is. But now if I want to mention that who has sent the message, can I make an authentication of that as well? About the sender itself. That is where it requires the message authentication code. Okay, so it's basically kind of a user authentication code to be specific. The name should have been user authentication code because the message is encapsulated by a hash function. We are sending it, but now using this, we are trying to find out whether the user is authentic or not. So that is being done over here. So for that, we call it something like this. You can see Alice needs to provide proof that it is Alice sending the message. Suppose I send the message from my ID, that means that I have made the message myself. I have my own set of structure based on which I have sent you the message. So that's basically what the MDC is all about. So the MAC is all about. You can see data origin authentication. So how it works, it's something like this. Why it is advantageous? You see the structure over here. This is using only hash function. In that, what we are trying to do, we can observe there are two channels that we have to consider. One is the insecure channel through which we are sending the data, but there should be a channel immune to change through which we are going to send the secret keys and all other stuff. through that process. So hash function actually thinks of this way. But as I said again, it doesn't guarantee that the user is authenticated or not. So for that user to get authenticated and to reduce the dependency of two such channels, we will take the help of MAC, which will take only one insecure channel. So that's my one channel. What it does, simply, very simple operation, it uses just a key. A key that will identify the user. Don't think that this key is the private key, public key. That is for the encryption side. This is for the key for the user authentication. Only for the user to authenticate that the message has been sent by him or not. So that's basically the key in the left hand side that you're looking at. So in that way, what is happening at the receiver end, the Bob, the intended user, who will also have the knowledge of this secret key for that particular user. Based on that, it will decipher the message as well as it will check the MAC. Alright? And if the MAC is also correct, then it will accept it's like a two-stage authentication we are doing. One, we are checking the message itself using the hash function, and we are also ensuring the integrity of the user is vendor. Okay, so that's the basic thing we are doing at the input. Along with that, we are doing another encapsulation of encryption using the DES and the AES strategy, and then we are sending it over the channel. Even after that, the data gets hacked and we get the data to be leaked in internet. Alright, so that's the problem with it. But this is what we are trying to achieve using this MAC. So to achieve that, let me just finish off on that note. Usually the two ways of doing it is prefix MAC or the postfix MAC, where a certain set of bits, just like zero padding, it will be added prefixed or postfixed. So let me show you the diagram itself directly. This is called as nested MAC. So what is happening? The message is over here. Hash is generated. We are adding a key. You can see the key is over here. Key and the message makes the hash to be secret. But on that intermediate digest, we generate another set of operation, which is we are calling as a MAC. And finally, the hash is generated, which we are sending it over as the name MAC. So the hash function is not the similar hash that we have done so far. Hash function is generated using the SHA 512 or the Whirlpool technique. But that is hash function. But on top of that hash function, we are going to use a secret key, which makes that hash function to be named as MAC. So this plus the message will go to the receiver. From the receiver, the MAC will be segregated, the message will be segregated, the message will be tested whether it is correct or not, based on whether the hash function, the previous hash function is matching. Similarly, the MAC also needs to be checked whether the MAC is matching with the original one. Both of these authentications, if it is correct, then only we will consider the data is. So this is called as nested MAC and this is called as hashed MAC. Let me stop at this point. I think it will be too much for you for the time being. This is what we call as the hashed MAC or HMAC. So when we come back on Monday, we are going to start with the post process of MAC and this segment.